Hmm. Hmm? Hmm. Hello everyone. Welcome you all again to the last day of 1 week long ongoing Indo-Canada Spark Student Research Conclave on RF Energy Harvesting Systems, SRC 2020, organized by NIT Silchar in association with DTU Delhi and Queen's University, Canada, and hosted by Electronics and Communication Engineering Department, NIT Silchar. I extend my warm welcome to the first and last speaker of today's session, Dr. Partha Pritham Shom, who has just completed a PhD degree 2 months back from NIT Silchar. Partha Pritham Shom received the BTech degree in Electronics and Telecommunication Engineering and MTech degree in Communication System Engineering from KIIT, deemed to be University, Bhubaneswar, India. In 2020, Partha received his PhD degree in Electronics and Communication Engineering from NIT Silchar, India. His current research interests include multifunctional microwave circuits, reconfigurable antennas, multiple antenna systems, ultra-wideband filters and antennas. He has authored or co-authored 10 papers in different peer-reviewed journals at conference preceding of national and international. He is an active member of the IEEE Antenna Propagation Society and IEEE Microwave Theory and Technique Society. With this, I welcome and invite to Dr. Partha to start the session.
Hello, sir. Am I audible?
Yes, you are audible.
Okay, sir.
You share your presentation. Yes.
Is my PPT visible now?
Yes.
Okay. Thank you, sir. Thank you very much for the nice introduction and also for giving me this opportunity to deliver a talk in this Student Research Conclave 2020. So first, a very good evening, good afternoon, and good morning to everyone who all are present at this moment through this virtual platform. The topic for today's talk is filter circuits for RF energy harvesting and wireless power transfer systems, concepts and opportunities. The content for today's presentation is going to be as follows. First, a brief mention of energy harvesting. Then I shall jump to the concepts of RF energy harvesting and its importance, followed by the concepts of wireless power transfer systems. In the past 4 days, different speakers have discussed in detail about the fundamental concepts related to energy harvesting as well as wireless power transfer systems. So I'll only make a brief mention of those topics just to recall the fundamental aspects. Next, in order to implement the RF energy harvesting and wireless power transfer system, we need to use rectenna circuit. So we'll also have a glimpse to the related concepts on rectenna. Next, we'll switch to the need for filter circuits in EH and WPT systems. Finally, a review of the design techniques for filter circuits, followed by a discussion on our own research work related to filter. In the session 1 of day 1, Dr. Nita has explained the need and advantages towards the trend of shifting from wired network to wireless network mode. In wireless communication mode, although energy supply is always a critical issue, the recent advances in technology have led to the development of Internet of Things, wearable electronics, 5G wireless systems, etc., which requires widespread deployment of sensors, often positioned at remote places. And power is often a limiting factor, as we have to depend on battery sources to power up the devices required for these communication systems. Now the batteries usually have limited capacity and need to be physically charged or replaced periodically. Therefore, in order to have some sustainable autonomous batteryless wireless system, we should have some alternate solution. Nikola Tesla dreamed of a day when all equipment requiring electrical energy would pull that energy from the air, either from directed wireless power sources or ambient energy harvesting. Some called him a visionary, while others called him a charlatan, but many do attest that his early vision of alternating current his early vision of alternating current transmission systems and wireless power transfer systems are the precursors of today's energy harvesting technology. So first is energy harvesting. Energy harvesting, also known as energy scavenging, is the process by which energy is derived from external sources, captured and stored for operating autonomous devices. In general, energy is transported through the ability of matter or waves to carry a force within a medium such as water, air, or solid materials. In energy harvesting, the ultimate goal is to intercept this transported force and convert it to electrical energy. This is achieved by applying the transported force to a transducer, which basically converts the energy from one form to another. And then by employing the transducer, we can extract the desired electric current or desired electric current. Now, depending on what originates and transfers the force and which medium is used during the transportation, energy harvesting can be broken down into different categories like solar energy harvesting, then vibrational energy harvesting, wind energy harvesting, thermal energy harvesting, and radio frequency energy harvesting. In solar energy harvesting, the source of energy is the photons that the sun generates during the nuclear reaction inside the sun. Now, these photons travel from the sun to this earth in form of electromagnetic waves and are intercepted by the solar panels that turn photons into electrical energy. On the other hand, in vibrational energy harvesting, it is a viable alternative to provide power for sensors in areas that have sufficient vibrational activities. Some of the examples of the vibrational energy harvesting system includes seismic activities areas, subways, cars, then industrial machinery, and raindrops on tree leaves. Next, to harvest the wind energy, and we usually use an electric motor which contains a magnetic rotor. This setup facilitates the conversion of mechanical energy of the wind into the rotation of motor, and then which induces the necessary electromagnetic force on the rotor. This electromagnetic force is then is the harvested energy in the form of an electrical current. Although small-scale turbines are available for embedded circuits that produces a power output in the milliwatt range, this technology, harvesting technology, is much more common for producing output in the kilowatt range and less common for like milliwatt application. Now, out of all these energy harvesting techniques, the RF energy harvesting technique is like one of the common and easy approaches for harvesting energy because of its continuous availability. However, there are some limitations with RF energy harvesting, which is basically like it suffers from low incident power levels. So this limitation can be overcome by using a dedicated source or an efficient RF to DC conversion circuit. RF energy harvesting basically is an energy conversion technique which is used to convert energy from EM field into the electrical domain, that is into voltages and current. the amount of RF energy that can be harvested depends on the wavelength of the harvested RF signal, and also the distance between an RF energy source and the harvesting device, which can be calculated using the Friis transmission equation. These are some of the common applications, consumer applications, where the RF energy harvesting technique is used to capture or harvest energy and then power these like handheld portable communication devices. Next is wireless power transfer. The wireless power transfer is a technique that is used to transfer energy from one point to the another without any wired media link. The idea of wireless power transfer has been around since the inception of electricity. In late 19th century, Nikola Tesla described the freedom to transfer energy between 2 points without the need for a physical connection to power a source. A truly wireless device capable of being remotely powered not only allows the obvious freedom of movement, but also enable devices to be more compact by removing the necessity of a large battery. Now, radio frequency energy harvesting and radiative wireless power transfer system have attracted significant interest as methods of enabling battery-free, sustainable wireless networks. In implementing RF energy and WPT, rectifying antennas are the cornerstone of these techniques, and it critically affects the amount of DC power that is delivered to the load. The crucial stages in implementing the rectina are designing an efficient antenna circuit and then a rectifier circuit. The performance of the rectina usually relies on the performance of both the components, that is antenna and the that is the harvesting ability of the antenna and the power conversion efficiency of the rectifier circuit. In the past years, extensive research has been carried out in the field of rectina designing to develop different configurations of rectina circuit. In general, the rectina system consists of an antenna, then rectifier circuit, then we have a matching network and the resistive load. The antenna basically is to sense and receive the RF energy, and then the rectifier converts the RF signal into DC signal. The matching network is basically required between the antenna and rectifier circuit for maximum power transfer, such that the impedance between the two circuit components matches. Irrespective of the application, the basic functioning or the basic structural diagram of the rectina system remains almost same. Now, next we'll move to the concept of filter or the need of filter in retina systems. Now, in retina system, the rectifier circuit includes diode, which is a nonlinear element. These diodes generate harmonics of the fundamental frequency. In most of the practical systems, these harmonics gets radiated from the antenna, which decreases the efficiency of the rectifier in the conversion of RF to DC. So to avoid that, we need to incorporate one bandpass filter in between the rectifier and antenna. So in this slide, you can see that this is the conventional retina systems, which comprises of the antenna, matching circuit, rectifying circuit, and resistive load. And this is the advanced retina systems where we embed and bandpass filter so that this harmonic issue can be resolved. Now, in order to reduce the size of this overall rectifier system, it is suggested that we can combine the antenna and bandpass filter into one single functional module. This type of topology is usually called as filter. So this is one of our works where we have reviewed the fundamental concepts of filter and listed out the different topologies available for designing filter circuits for RF front-end system. The work has recently been published in the journal IEEE Antennas and Propagation magazine in the month of May. Anyone who is interested can go through this paper to get the idea related to filterness in detail. We have tried our level best to combine all the necessary concepts as well as technical advancements related to the filterner designs in like 10 or 12 pages. Next, the concept of filterness. The popularity of wireless communication has contributed to an increasing demand for next generation compact wireless devices for use in wearable and as well as portable applications. These requirements have promoted the need for the miniaturized devices which can be like we can put miniaturized handheld devices which we can put and can easily port port from one position to another. So designing communication blocks with multiple functionalities which are like low profile, low cost and compact in size is therefore attracting interest to meet this trend of miniaturization. In Rectenna systems, we have seen that the antenna and bandpass filter are two essential components and are widely designed for use in the like front end of Rectenna systems. In this context, filtering antennas have emerged as a potential solution to minimize the complexity, size, and cost of this like Rectenna front end systems. Filterners are designed to support both filtering as well as radiation phenomena in a single unit. Advanced filterner designs rule out the need for designing and integrating antenna and bandpass filter structures individually, thus creating a more compact structure and eventually improving the performance of the entire front-end network. The capability of filterners in suppressing the out-of-band radiation also benefits in the reduction of mutual coupling that arises between an antenna and other electrical devices. However, it is always challenging to design a antenna circuit that exhibits multiple functionalities, which in this case is of both the antenna as well as of a bandpass filter. Now, these are some of the advantages of filterners, which includes like it exhibits both filtering as well as radiation properties. Then it reduces the interconnection losses that occurs when an antenna is like explicitly connected to a bandpass filter. Also, it suppresses unwanted signals out of the operational band. Then it facilitates a more compact and low-cost RF front-end system. Then it reduces the design complexity of the integrated systems. Based on the study of the existing literature, we have identified that the filterner can be classified based on the design techniques in 4 categories. Like one is traditional approach, then the filter synthesis approach, co-design approach, and fusion approach. In traditional approach, the filtering circuits are cascaded to the antenna directly or through a matching network. The co-design approach achieves filtering and radiation characteristics in a single subsystem by embedding filtering structures into the different parts of an antenna without hampering the radiation performance and gain characteristics. This co-design technique reduces the transition losses that occur in the traditional filter structures when we need to like include one additional matching circuit. On the other hand, the filter synthesis approach is utilized in designing filterners where the last stage resonator of a bandpass filter is replaced by a radiating element. In all of these designing techniques, that is the traditional approach, filter synthesis approach, and co-design approach, an additional filtering element must be integrated to the antenna circuit to achieve the filtering characteristics. This introduces additional insertion losses and thereby limits the antenna from achieving a high gain performance. To overcome this limitation, an alternative technique has been proposed in the literature, which is called as the fusion approach. The fusion approach realizes filtering antennas without employing any extra filtering circuit. Using these mentioned techniques, different configurations of filterners were reported for efficient integration of filtering and radiation properties into a single subsystem. These are the classification of the differently reported filterners available in the literature based on their structural mechanism. This includes traditional filter structures, DGS-based filter structures, coupling resonator-based filter structures, SIW-based filter structures, multi-layer filter structures, and reconfigurable filter structures. In traditional filter configurations, antenna and bandpass filters are designed individually and then integrated directly or through some matching networks for establishing the desired filtering performance characteristics. This approach has been used for designing filter NAS with varied range of fractional bandwidth and also suited for different frequency-based applications. The direct integration approach leads to several design complexities, such as strong coupling between the antenna and filter, and then bandwidth mismatch between the antenna and filter, since we are integrating them directly. These limitations then affect the radiation performance of the overall system. So on the other hand, we have an alternate approach where we can put some extra taper structure or matching network in between the antenna and filter. This helps in further enhancing the frequency selectivity by introducing radiational nulls and achieving radiation stability and polarization quality within the operating bandwidth. One of the commonly used techniques for designing filter NAS is to use DGS-based filters. In this approach, the antenna and filter structures are integrated in a single subsystem by embedding defector structures into the ground plane of the antenna. Now, DGS structures are beneficial in increasing the frequency selectivity and achieving harmonics rejection and out-of-band signal suppression. However, the slotted structures in the ground plane sometimes lead to back radiation, which can restrict the gain characteristics of the integrated filter antenna system. The next technique structures are coupled-based resonator structures, which are primarily designed based on the filter synthesis approach. This technique allows an antenna to behave like the last stage resonator of an loaded bandpass filter. The other type of structures are SIW-based filter structures. SIW structures are one of the recent technologies that have been widely explored in designing high performance antennas as well as high performance band filters. SIW structures have the advantages such as high power handling capacity, then reduced level of insertion loss, low cost, and easy integration with planar microwave elements. By virtue of the high Q property, and SIW structures can be successfully used for narrowband application. The ability of the SIW filter NAS to operate on frequencies greater than 10 gigahertz makes them a favorable candidate for future wireless applications. The next type of structures are multi-layer structures. In multi-layer structures, these structures can reduce the overall footprint of the filter circuits and eliminate the need for installing any extra filtering circuits in the overall integrated system. The superiority of this technique is that it can achieve a higher degree of frequency selectivity. Further, since no additional filter circuits we need to include in this type of structures, it can achieve high gain performance, like usually greater than 6 dBi. The final type of structures are the reconfigurable structures. Reconfigurable microwave circuits are considered as a potential candidate to maximize the functionality and to overcome the limitations of a congested spectrum environment. These structures have the ability to alter the functioning based on the changing radio environment by modifying their equivalent electrical configuration. So these are the classification of some of the commonly available filter structures based on their structural property. Next, we'll be discussing about some of the filter design examples that has been proposed for both RF energy harvesting application as well as wireless power transfer system. So this is one example which has been proposed by Yeo et al. In the year 2015. In this work, the authors have designed a compact half ring shaped slot antenna, which is fed by a CPW transmission line for achieving the harmonic suppression functionalities. The antenna consists of an HRS slot, half-ring slot, and stepped impedance resonators, which are symmetrically connected to the slot at both the ends. The two SIRs are used to suppress the harmonics of the fundamental resonance frequency, with an additional advantage of with providing an additional advantage where we can achieve a miniaturization by incorporating this stepped impedance resonator. This is the design process of this particular like half ring shaped slot antenna. Initially they have designed one CPW fed antenna with a rectangular slot. Next, to miniaturize as well as have efficient performance characteristic, that rectangular slot they have upgraded into an half ring slot connected with two step impedance resonator. So this is the fabricated prototype. This is the fabricated prototype. Then we have the comparison of simulated and measured input reflection coefficients of the fabricated antenna. At the first resonance frequency, both for simulation as well as measurement, especially for the measurement, the VSWR is less than 2 within the frequency span of 2.36 to 2.53 gigahertz. This particular result has been obtained for the rectangular slot antenna. That means for this particular antenna. Next is the bandwidth for the this HRS slotted antenna. In this case, the bandwidth is from 2.39 to 2.49 gigahertz. In this case, the fractional bandwidth achieved is 4.1%. Both the conventional rectangular antenna as well as the proposed slot antenna satisfy the frequency band requirement for 2.455 gigahertz band application. By like removing this rectangular slot with this half ring shaped slot, the authors have like realized reduction in size by almost 45% in by almost 45%. Then there is the measured radiation patterns of the proposed antenna in the YZ as well as in the ZX plane at 2.45 gigahertz. This has the measured performance has also been compared with the simulated one, and the like the patterns are almost similar that of a typical slot antenna. The next design example is of a high efficiency broadband rectina. In this work, a broadband rectina for ambient wireless energy harvesting application has been proposed, which can operate in the frequency span of 1.8 to 2.5 gigahertz. In the design process is something like that. Like the authors first have studied the characteristics of the ambient radio frequency energy available in the their nearby environment. The results are then used to aid the design of a new rectina. The authors have also proposed a novel design of two branch impedance matching circuit to enhance the this is the impedance matching circuit to enhance the performance and efficiency of the retina, even for a low ambient power level. Also, they have proposed one broadband dual polarized antenna, which has a flower shaped flower shaped slotted radiator. Next, the authors have implemented a flower-shaped, an H-shaped slot filter in the antenna patch, which exhibits a harmonic rejection property and can also reject the higher order harmonics to further improve the retina efficiency. This is the rectifying circuit that the authors have proposed. The rectifying circuit has two branches. The upper branch consists of a radial stub, a shorted stub, and a 6 nanohenry chip inductor, and this is aimed for getting the necessary matching at 1.8 and 2.5 gigahertz. Then there is a lower branch that consists of a band short stub and a 1.8 nanohenry chip inductor, and this is aimed to get the circuit matched at around 2.1 gigahertz. There are 4 chip inductors that are used, and the values are chosen as 100 nanohenry. Also, the authors have used two Schottky diodes to achieve the rectifying characteristics. For rejection of higher order harmonics, an H-shaped slot is produced on the ground plane of the antenna microstrip feed line, which is at the back, and it is orthogonal to the antenna feed, as shown in this figure. The impedance at the second and third order harmonics can be changed by modifying the size and position of this H-shaped slot. The performance figure shows the level of the performance figure shows the suppression level for the proposed antenna configuration. Next, during experimentation for evaluating the performance of the new broadband rectina, authors have selected a typical indoor office environment which has a relatively low ambient RF power density. First, they have used they have used the proposed antenna alone and a spectrum analyzer to measure the amount of the received power. The typical received power can be seen in this particular figure. The power levels are maximum near the frequencies like GSM 1800 4G, which is used for 4G band, then UMTS 2100, which is used for 3G, and then Wi-Fi bands. The input power levels over the entire band is around minus 37 to minus 32 dBm. Next, the antenna was replaced by the rectina they have proposed, and they have measured the output voltage using a voltage meter, as shown in this particular figure. The measured voltage level they have found to be equal to 250 in the range of 250 to 300 millivolt. The power level over the entire band was found to be in the range of minus 25, which is higher than the initial power level of minus 37 to minus 32 dBm. The measured overall conversion efficiency against the different load is depicted in this figure, and it can be seen that the highest conversion efficiency of around 16.6% is achieved when an optimal load of around 15 kilo ohm has been used by the authors. Next is the example of a of a filter circuit for WPT application. In this work, which has been published in IEEE Transaction in the year 2014, the authors have proposed 2 different configurations of harmonic rejection filter with coplanar waveguide feeding mechanism for 5.8 gigahertz application. The antenna structure that they have used is a conventional CPW for rectangular monopole antenna. What they have done, they have modified the feeding network with 2 different CPW based compact microstrip resonant cell structures. This one and this. In the first topology, the blockage or the filtering characteristics is realized by using a CMRC in combination with an U-shaped slot. And again, in the second topology, a pair of strongly coupled CMRC structures has been implemented and optimized to achieve the necessary filtering characteristic. Now, both these new feeding mechanisms are realized in prototypes and experimentally they have validated it. The measured antenna return loss at the second and third harmonics is in the order of 0.5 and 1.5 dB respectively, which corresponds to return loss suppression of around 4.5 dB in compared to this reference monopole antenna. Both of these antennas have realized fractional bandwidth of around 18%, which is quite laudable at that time when this article was published. This is the radiation characteristics of the proposed work. So now finally I would like to discuss about some of our findings related to field antenna designing. So this is one work where we have designed a compact configuration of field antenna for cognitive radio systems. The work has recently been published in the journal IET Microwaves and Antennas and Propagation. It can be found in the volume 40 number 10 in the month of August 2020. So initially, I will describe about the configuration of field antenna design, field antenna that has been designed for UWB application. This is the schematic layout of the field antenna circuit. The filtering unit, it has two main constituent parts: the filtering unit and the radiating unit. The filtering unit employs a multiple mode resonator structure, which is designed using a stepped impedance stub loaded resonator to achieve wide filtering characteristic. Then on the other hand, we have an elliptical shaped radiator to achieve the necessary radiation characteristics. The salient feature of the geometry can be seen in the slide itself. In the bottom layer of the field antenna, we have used partial ground plane structures with apertures in the ground plane to provide the necessary strong level of coupling to the MMR resonator and the input output interdigital coupled lines. We have used also the FR4 substrate of thickness 0.8 mm for designing the field antenna structures. The other details like dimensions and all related to this proposed geometry can be found in our published article. The simulated and measured S11 performance can be seen here. The simulated bandwidth has been noted to be 3.45 to 10.69 gigahertz, and the measured bandwidth is from 3.41 to 7.8 gigahertz. There are total 4 resonances which has been observed both in simulation as well as in measurement, and these 4 resonance frequencies are at 4.23, 6.30, 8.20 and 10.3 gigahertz respectively. There is a very good agreement between the simulated and the measured data. Next, in order to analyze the performance of the field antenna design, we have divided the geometry into its constituent antenna and a filter unit. First, we have designed one monopole antenna using the same radiator that we have used in our field antenna design. The fabricated prototype of the field antenna of the elliptical antenna can be seen here. We can see that this is a simulated and this is a comparison of simulated and measured performance. We can see that the antenna exhibits wide bandwidth characteristics covering the entire UWB band. However, the selectivity of the antenna is very poor towards the higher frequency end. This type of drawback is observed in most of the wideband antenna structures. This poor selectivity of antenna limits the capacity of antenna in efficiently suppressing the spurious harmonics and rejecting out-of-band interferences, which is usually created in the transceiver circuits. So to overcome this poor selectivity, a bandpass filter need to be accompanied by this elliptical radiator. In our work, we have attempted to achieve those characteristics only within a limited circuit area. Also, we can see that the radiation characteristics of the proposed elliptical radiator, and it is uniform throughout the complete operating bandwidth of the antenna. We have obtained the radiation characteristics at 3.5, which is the lower end of the bandwidth, and 10.1, which is the higher end of the bandwidth. And the radiation characteristics remains almost uniform throughout the operating bandwidth, which establishes the radiation stability of this particular elliptical radiator. Next, to analyze the performance of the filtering resonator, we have designed one bandpass filter using the same MMR structure. We have tried to examine the resonance characteristics both theoretically as well as through simulation software. Since the resonator unit, like this structure of the filter is symmetrical, therefore odd-even mode analysis approach can be we have used for numerical characterization of the MMR unit. This odd-even analysis approach simplifies the analysis of symmetrical microwave circuits by dividing it into two subunits, that is the odd mode unit and even mode unit, along the plane of symmetry. Next, by applying suitable conditions to each unit, the resonance conditions can be correctly obtained. So this is the equivalent representation of the MMR unit in terms of its characteristics, admittance, and electrical length. So for odd mode excitation, this a plane of symmetry, it becomes short circuited, and this is the odd mode equivalent circuit. Similarly, for even mode case, the plane of symmetry becomes open circuited, and the equivalent circuit becomes the equivalent circuit becomes something like this. Now, by applying the condition of resonances, we have derived the resonance frequencies graphically using MATLAB. These are the set of equations that has been derived for the odd mode case, and this is the graph that we have derived to obtain the solution. We can see that in the frequency span of 2 to 14 gigahertz, the resonator exhibits two resonances if odd mode excitation is applied. The same procedure has been followed for even mode analysis, and we can see that in this case the resonator exhibits 3 resonances within the span of 2 to 14 gigahertz. That means altogether we have a 5 resonances. We have also verified this using commercially available simulation software. For that, we have maintained weak coupling across the MMR resonator, and we can observe that under weak coupling, the resonator exhibits a total 5 resonances. Next, to achieve strong coupling, which is essential for obtaining good passband characteristics, we have increased the coupling length up to an equivalent length of lambda by 4, which is approximately 7 mm in our case. We can see that a good passband characteristics shown by the black line has been achieved for our proposed case. We have also investigated the role of ground plane apertures, and you can see that in this figure that it has a great role in exciting the resonant modes appropriately. We have also done fabrication for the filter prototype and have obtained good agreement between the simulated and measured performance. Next, to understand the operating mechanism of the filtering antenna, we have obtained the current distribution at 3 different frequencies: 2 gigahertz, which is below the lower cutoff frequency of the desired band; then at 6.85 gigahertz, which is the center of the desired band; and at 12 gigahertz, which is above the upper cutoff frequency of the desired band. We can observe that at 2 gigahertz and 12 gigahertz, in 2 gigahertz and 12 gigahertz, the surface current remains concentrated near the stepped impedance stub loaded resonator, this structure. and no current can reach to the elliptical radiator, whereas surface current is found to be distributed near the feeding point to the elliptical radiator when we simulate the surface current distribution at 6.85 gigahertz, which helps in achieving radiation phenomenon at that particular frequency. Also, we have compared the simulated performance of the filter now with the elliptical radiator based monopole antenna and the UWB filter. It is observed that the bandwidth and the frequency selectivity of the monopole antenna improves substantially after integrating the bandpass filter into it. The overall bandwidth of the filter is mainly contributed by the selectivity of the bandpass filter. This is the fabricated prototype of the filter now. Next, we have extended our filter design to develop a circuit for cognitive radio applications. Cognitive radio technology is a modern approach adopted to overcome the limitations of spectrum scarcity in contemporary wireless system. In a SEER application, the radio environment is continuously monitored to sense the occupancy and identify unoccupied wireless channel within a frequency band. Filterna with wideband to narrowband reconfigurable functionality find potential implementation for SEER application. The wideband operating state is used for spectrum sensing purpose, whereas the narrowband state is employed for communication functions. The proposed filter design is therefore modified by incorporating frequency reconfigurable properties such that it can be tuned between UWB and C-band state of operations. Here we can see the resultant geometrical layout to introduce the reconfigurability. The low impedance line section of the of the MMR structure is loaded with two vertical open-ended stubs and embedded with two pin diodes. These two stubs are placed symmetrically at an equal distance from the central loaded stub. This results in shifting the operating range of the filter from UWB to narrowband range which is targeted for mainly C-band applications. This is the fabricated prototype of the reconfigurable filter. The switching between the two states is achieved by employing a pin diode SMPA 1320079LF, which is produced by the Skyworks. The equivalent circuit model of pin diode in on and off mode condition can be seen here. When both the diodes D1 and D2 are kept in the reverse bias condition, that is in off mode, the filter works in UWB state of operation. And likewise, when we forward bias condition is applied, that is the on condition is applied, the system operates in the C-band state of operation. There is the performance matrix of the filter, both in UWB as well as C-band states. The interesting part is the gain and efficiency curve, where both the gain and radiation parameters fall drastically outside the operating bandwidth due to the presence of the filter structures. All the performance parameters are well within the acceptable limits for commercial implementation. This is the radiation characteristics of the proposed reconfigurable filter. The radiation pattern has been noted when the filter was operating in the UWB state at two different frequencies, 4.3 GHz and 10.3 GHz. So as a part of a conclusion, we have seen the concept of filter for in context of rectenna systems. Then we have also learned the different design techniques and the different structures that are available in the existing literatures. We have also seen some of the filter design examples that has been proposed for RFEH and WPT systems, and also we have learned about the Filtena configurations with reconfigurable functionality, which is suitable for CR system. There are some works which are currently in the pipeline, where we are trying to extend the use of this reconfigurable Filtena for RFEH and WPT application. So these are some of the articles which I have referred during the preparation of my presentation. So thank you everyone. Stay safe in this time of pandemic. And at the end, I would again like to thank my supervisor, Dr. Taimur sir, for inviting me and giving me this opportunity to share my research findings in this 1 week long SRC on RF energy harvesting. Thank you, sir.
Thank you, Dr. Partha, for making us aware about Filtena concept in context of RFEH and WPT. There are few queries based on this lecture. First one is how to find out place and structure of slot for harmonic frequencies.
Pardon, sir? How to find out?
How to find out place of slot for harmonic frequency rejection, basically.
This there is no hard and fast criteria or guidelines to place the slots. It basically varies from structure to structure. We can use it in the radiator also, or there is one example I have shown for WPT where the authors have used it in the ground plane. So there is no hard and fast rule.
Okay. Now next query, why we use Filtena in place of multiband antenna in RF energy harvester?
Why you use Filtena
in place of multiband antenna in RF energy harvester?
Filtena as such has no role with the band of operation or number of frequencies.
Ultimately, I think his intention is to know why we use Filtena in RF energy harvesting or WPT, because so many speakers have described the need of Rectena, different design concepts of Rectena, and all other things. But today he is listening that there is a possibility of Filtena incorporation in Rectena. So then, what's the need of that one?
Yes, as I have mentioned that in Rectena we use that we have a rectifying unit where we use diodes, which is have a nonlinear performance characteristics. So these diodes sometimes they create unwanted harmonics, which may get irradiated through the antenna. So this irradiation then affects the efficiency of the receiving this irradiation affects the harvesting ability of the antenna. So to avoid that creation of harmonics and backward movement towards the antenna, we place a filter structure in between antenna and filter. Now the Filtena is to have a compact version, which is the need of this present time, the miniaturization, which is the primary need. So Filtena is a concept that satisfies this need.
Okay, I think your answer will be justifying the queries of the respective participants. Now finally, thank you very much, Partha, for your informative session delivery, covering different aspects of Filtena in context of the RFEH and WPT. With this, I am paying my thanks to you again for accepting the invitation and for delivering the lecture. Thank you, Partha. See you in the validatory session scheduled today at 9 p.m. as per our time zone. Okay?
Yes, sir. Okay.
Bye. Bye.
Thank you, sir.
Okay. Now, I request to all the registered participants to go for the mandatory MCQ test using the link already emailed you as well as shared in the Google Meet chat box. And after completing the MCQ test, all the participants are also invited for attending the valedictory function on the same Google Meet platform. The Google Meet link will be restricted to only first 60 participants, and this facility will be available on first come first served basis. Please go ahead for your MCQ test. Bye. Good evening, Professor K.L. Vaishnav, sir, and welcome to this valedictory session.
Hey, very good evening. Very good evening. I can see
sir.
Professor Raghavan sir also there.
Yes, sir. Yes. Good evening, Professor Raghavan, sir.
Maybe. Okay. Okay. We are ready.
Okay, yes, sir. Within 5 minutes, sir.
Thank you.
Director, sir, and others are about to join. Good morning, sir. Professor Yaya Anton, sir, good morning.
Good morning, everybody. You hear me, Taimur?
Yes, sir, I can hear you. Welcome you, sir, for this valedictory session.
Thank you. Glad to be here and join all of you. It's interesting.
Thank you, sir. Good evening, Ashok Day, sir. Good evening, Ashok Day, sir. Good evening, Director, sir.
Good evening. Good evening. Oh, there are so many people. Professor Antar, good evening. I think good morning to you, Professor Day.
Yeah, good evening. Good evening to you. Good evening to
Yeah.
Professor Day.
Yeah.
Good morning, Professor Antar.
Good evening, sir.
Director, sir, can I proceed for?
Yes,
Okay,
obviously.
Everybody has
Yeah.
joined now. Okay.
Mm-hmm.
Hello, everyone. Myself, Dr. Taimur Khan, on the behalf of organizing committee, is going to start the valedictory session organized after successful completion of 1 week Indo-Canada Spark Student Research Conclave on RF Energy Harvesting Systems, SRC 2020. Respected Director, Sir, Professor Shivaji Bandyopadhyay, Dean Research and Consultancy, Professor M. Ali Ahmed, Institute Coordinator Spark, Professor Upendra Kumar, Head of the Electronics and Communication Engineering Department, Professor K.L. Vaishnav. Entire team of Spark project, all invited student speakers, organizing team of SRC 2020, esteemed colleagues, friends, and dear participants. Good evening, good morning, and good afternoon to one and all present over here. On the behalf of organizing committee, I welcome you all for this valedictory session conducted after successful completion of this 1 week long Indo-Canada Spark Student Research Conclave on RF Energy Harvesting Systems, SRC 2020, organized by National Institute of Technology, Silchar, in association with DTU Delhi and Queen's University, Canada, and hosted by Department of Electronics and Communication Engineering, National Institute of Technology, Silchar. It has been a wonderful experience of organizing this 1 week long Indo-Canada virtual SRC in this ongoing global COVID-19 pandemic situation. Several new things have been learned during the whole period of SRC 2020, how to use the digital platform for such a massive gathering effectively. A specific aim of organizing SRC 2020 was to provide a mutual platform to the student researchers working or wish to explore their research in the area of RF energy harvesting in different allied applications. The SRC 2020 has successfully addressed several fundamental concepts related to the recent development pertaining to RF energy harvesting. At the same time, it has included in-depth discussions on various design challenges that are encountered in this field and their possible solutions. The SRC 2020 has provided not only the essential knowledge, but also a platform to the participant for exchanging their ideas and information with the respective invited student speakers having same level of knowledge or slightly higher than their own knowledge. Total 11 student speakers, including Mr. Sem Gosen from Turkey, Mr. Kasan Dotov from Kazakhstan, Ms. Neeta Singh from JNU New Delhi, Mr. Vikrant Kayam from JNU New Delhi, Ms. Libby Divakaran from APJ Abdul Kalam Technical University, as well as our internal PhD students, including Debanjali Sarkar, Osir Pratham, Mohammad Ehsan Halimi, Dasti Surendra, Ashutosh Srivastav, and Partha Pritam Shom, all belonging from NIT Silchar, have successfully delivered talks in their respective fields of expertise. Now, I am proceeding for vote of thanks. Honorable Director, entire team belonging to the Spark project, invited student speakers, organizing team of SRC 2020, esteemed colleagues, friends, and dear participants. I, Dr. Taimur Khan, the convener of SRC 2020, consider it a great honor to propose the vote of thanks to all of them who has helped us in making this virtual event a grand success. As a convener of SRC 2020, firstly, I would like to propose my vote of thanks to the Ministry of Human Resource Development, presently Ministry of Education, Government of India, for funding this research conclave under ongoing SPARK project. In the continuation, I must now mention my heartfelt thanks to our respected director, Professor Shivaji Bandyopadhyay, for giving us an exposure to conduct this student research conclave. He has always been a source of motivation and encouragement as well to do something new in the department for the overall development of the institute. Next, I would like to propose my sincere vote of thanks to Dean Research and Consultancy, Professor M. Ali Ahmed, Institute Coordinator SPARK, Professor Upendra Kumar, Chairperson of SRC 2020, Professor K.L. Vaishnav, for extending their supports for making this event a grand success. Next, I would like to pass my warm welcome to the entire SPARK team involved, especially Professor Yahya Antar, Professor Frondorfer, Professor Ashok Dey, and myself, Dr. Taimur Khan, whose collective efforts have made this research conclave possible. Next, my sincere gratitude to all the invited student speakers from India as well as from abroad. Sem Gosen from Turkey, Kasan Dotov from Kazakhstan, Neeta Singh from JNU New Delhi, Libby Divakaran from APJ Abdul Kalam Technical University, and Vikrant from JNU New Delhi, as well as our internal PhD students, including Debanjali Sarkar, Osir Pratham, Mohammad Ehsan Halimi, Dasti Surendra, Ashutosh Srivastav, and Partha Pritam Shom, all belonging to NIT Silchar. Thank you all for your accepting our invitation and agreed to share your knowledge with the participants in their respective areas of expertise. As no program becomes successful with a single person, so I extend my big thanks to the entire organizing team associated with SRC 2020, especially Dr. Naresh Babu, Assistant Professor from CSE Department, and our students Dasri Surendra and Suman Modak, for managing different activities associated to this digital platform on which we all are connected this evening and was remain connected for the entire duration of 5 days of this virtual event. In last but not least, I extend my warmest welcome to all the participants belonging to different parts of the globe, irrespective of their different time zones, who have registered for this student research conclave and enjoyed all the sessions and have made this virtual event a grand success. Now, feedback is a very much important component to judge the success of an event. Keeping that in mind, I, on the behalf of organizing committee, would like to hear the overall perception from the invited student speakers about SRC 2020. Anyone interested, invited speakers may come forward to share his or her experience about SRC 2020. Any student speaker, please? Yes, Vikrant. Yes, please.
Yes, sir. Yes. Okay.
You
Good evening.
Yes, please. Go ahead.
Good evening, everyone. Before I say a few words about my experience here as a speaker as well as a listener, I would like to thank Professor Temur Khan and his dedicated Spark team for providing such a good opportunity to interact with some of the intellectuals who have presented their work on RF energy harvesting beautifully, and all the participants for listening patiently. Although there were many connectivity issues, but the interactive sessions were designed so beautifully that it didn't matter a lot. And such platforms should also come in near future to interact with people working in other research domain also. And overall, at last, I wish everyone to be safe and healthy in this difficult time, and hope we all could meet once again like before COVID. Thank you so much for listening patiently. Thank you so much, all
Thank you.
dedicated
Thank you,
team.
Vikrant. You also stay safe in this ongoing pandemic situation. Anyone else from invited student speakers?
Good
And
evening,
just
sir.
for a couple of seconds. Yes, please. Slebi Divakaran. Yes, please.
Good evening, everyone. I would like to thank Spark Organizing Committee and Dr. Taimur sir for inviting me to provide a talk on my area. While attending this conclave, not only I could express my ideas to the participants, but also as a participant, I came to know about various other areas or aspects where RF energy harvesting ideas should be improved. Many advantages as well as challenges in designing like computational intelligence. And on that area, I was not concentrated with all that areas were known to me. So such conclave should be conducted and furthermore so that many researchers can work in different areas jointly. So some many problems that are arising in today's environment can be removed. I wish everyone to be stay safe in this pandemic situation. Even though some connectivity issues were there for my presentation also, I would like to thank Taimur sir for patiently listening to me and all the help he had rendered me. Thank you, sir.
Thank you. Thank you, Dalivi. Anyone else from student speakers?
Hello?
Yes, please.
Yes, sir. Yes, sir. Good evening, good morning, and good afternoon to all. I would like to thank Dr. Temur sir and the dedicated team of NIT Silchar, as well as the team of Canada for organizing this seminar and give me the opportunity to speak and give my delivery of research on the topic of RF energy harvesting. And I also thankful to the participants who patiently watched and listened my research, because I also faced some network issue, and at last I'm very happy to express my vote of thanks to the team who made this seminar a grand success through their motivation and dedication. And I also looking forward to meet again and give such wonderful talk again. Thank you so much, sir. And to the participants also.
Thank you, Nita. Any last speakers from a student side? Last speaker from invited student speakers. Okay, no problem. Now, the participants' feedback is also equally important. In the end of valedictory session, each registered participant has to submit online feedback for the entire 5 days activities. In addition, we have created a Google Meet platform for around 50 selected participants so that they may share their observation about SRC 2020. Now, I request few participants to come forward quickly and share their experiences after attending SRC 2020. Participants, please. Any participants who wish to share his or her experience?
Hello, sir.
Yes, please.
Hello, sir. I am Arun Raj.
Your affiliation, you are from which institute, Arun Raj?
Arun Raj from Annamalai University, sir.
Okay. Yes, please. Okay. Please go ahead.
Yes, sir, I attended both webinars from RF energy harvesting webinar 1 and 2, and the DRE also I attended previous 2 weeks before. All the webinars are very nice, and I got more ideas about basics of RF energy harvesting and how to do that filter plus antenna, then rectifier plus antenna. And I am working in biomedical applications only, implantable antennas for biomedical applications. One lecture, I got more ideas related to my research work only. It is very excellent work. Thanks to Temur Khan sir for accepting me for this webinar. I am very happy to attending all the sessions. I got more idea about basics and my research work also. I got more ideas. Thank you for Temur Khan sir and NIT Silchar management from all experts. Thank you.
Thank you, Arun, for having a wonderful experience with us for the last 5 days. And any other participants, internal or external, from India or abroad? Anyone else? Please come forward fast to share his or her experience.
Hello.
Yes, please.
Yes. Greetings of the day, everyone. I'm Divakar Sharma, the pre-final year student of BTech undergraduate. I would like to thank all the team members here.
Please, your affiliation. You are from which institute?
I'm from Jamia Millia Islamia Central University, New Delhi.
Okay. Go ahead.
Whatever I have observed here in this RF energy harvesting conclave, it literally makes and created a curiosity inside to learn in this field for in future. And whatever few lectures are like the basic idea are explained in detail. And overall, I thank everyone here for making this happening. Thank you.
Thank you, Divakar. Thank you very much. Now, the SRC 2020 is organized by NIT Silchar in association with DTU Delhi and Queen's University, Canada. As per my sequence, it was supposed to invite Professor Yahya Antar, but I am not going to disturb him because of his some dental problem. Then I am moving to our Indian co-PI, Professor Ashok Dey, to share a few words on the successful completion of the event.
Good afternoon, everybody. Director NIT Silchar, Professor Shivaji Bandyopadhyay, Professor Antar, and other distinguished professors from the NIT Silchar, and all the participants. We are very glad that Spark project on energy harvesting, they have successfully completed number of programs within this last few months. And this program particularly was very important for the young researchers who are actively working in the field of RF harvesting to share their knowledge among themselves. And main feature was all the lectures were basically delivered by the researchers who are working particularly in this field. So all the participants and other co-workers who are also actively working in RF harvesting, they I am sure they are very much benefited from this 5 days program. I sincerely thank Professor Shivaji Bandyopadhyay for giving the Spark team to organize this valuable program and very important program on a very important subject of RF harvesting. And I am also very much grateful to Professor Y.M. Antar for actively supporting us. Thank you. And of course, I must thank Dr. Taimur Khan for organizing this particular program very efficiently. Thank you, everybody.
Thank you very much, sir. Thank you very much, sir, for your kind words and blessings for me. And now, in the continuation, I would like to call upon Institute Spark Coordinator, Professor Upendra Kumar, to speak a few words on successful completion of the event.
A very good evening to all of you. Honorable Director, Sir, Professor Shivaji Bandyopadhyay, Dean, Research and Consultancy, Professor M.A. Ahmad, HOD and Chairman, Dr. K.L. Vaishnav, Professor Ashok De, Professor Yahya, and Professor Prendorfer, and all the participants and all the expert speaker for this course. So I think this is the third course that Dr. T. Khan has organized in this Spark program. So this was a very successful program, and this particularly this course, I have seen that young research scholars, they have got the chance and they have very nicely explained their research ideas and whatever they are doing. So this has given them a platform to discuss their new ideas and new research, whatever they are doing. So we are seeing that in this particular area, that is electronics and telecommunication, is such an area that in 10 years, many things is changing and many advancements are there. So the things are very changing very rapidly. So new generations should come up and get acquainted with the ideas. And now the things are very interdisciplinary in nature. So they should take up the challenge and come to a solutions. And that is the aim of the Spark program. So one of the aim of the Spark program was to do this type of courses and workshop and to share the knowledge of our institute and the other foreign institutes and all from all the worlds where the students are joining. So they are also learning a lot. So this is one of the basic aim, which is very nicely satisfied in this Spark program. Then I have seen that this team has very efficiently published a book that is also a part of this research program, Spark program, to publish some books, monograms. So this is very nicely done. And I think the students, the research scholars, and our professors are working hard to get some patent or some very good research out of this project. So let us hope that the aim of this Spark program as a whole will be very efficient. And I would like to thank all the PI, co-PI, and their students for working hard. And for this particular program, I would like to thank Dr. Khan for his efforts and nicely arranging the program, and his team also. They have worked very hard. So thanks to all the team, thanks to all his students, and thanks to all the listeners and the speakers, participants. Thank you once again.
Thank you, Professor Kumar. Now I would like to call upon our Honorable Director, Professor Shivaji Bandyopadhyay, to say a few words on the successful completion of the SRC for the participants, for the organizing team, as well as for the participants.
Yeah, very good morning to Professor Antar, who has been our close friend since the project started. And so it will be continuing. Good evening to Professor De and other colleagues from NIT Silchar. And most importantly, the student speakers during this student research conclave, because that is a nice idea. That is the PhD, senior PhD students talking about their research to the student participants. So that peer level learning, that is what we give importance to. And the area itself, that is RF energy harvesting, say it is so important. I was just seeing that since the last Friday, I was in a condensed matter physics by national conference. So there, one of the areas were the RF energy harvesting. Then there was a faculty development program that I had to start. So that was IoT devices. There the issue of the RF energy harvesting was coming. Some discussions I had to do on the cyber physical system, where these devices or the things which need the RF energy, so how they can harvest that, what the traditional form of energy are not possible to be supplied to them. So that shows that both the theoretical areas as well as the practical implementations of this RF energy harvesting domain, from circuit design to materials and then to the various individual application domains. So the area is expanding, and I do believe that the kind of involvement that the Spark team, the Indo-Canada Spark team that has given on the number of programs they have organized, and more importantly with the students in focus. So that will bring us more, say, networking among the two teams. And so a lot of new activities, I think they are going to come in the near future. Wishing the success of the program, because from the feedback, it is quite clear that everyone was satisfied about the program. So more and more programs they are asking. Maybe the Spark by the middle of the next year, it will be over. But I think more collaborative programs will be there between the Indo-Canada team with NIT Silchar, DTU, and the Canada universities also. Thank you again, and good night to all of you.
Thank you, sir. Thank you very much for your motivating words for organizing team especially. And now, before concluding this valedictory session, I request everyone to please unmute your video. Sorry, sorry, I am extremely sorry for that. Now, finally, I would like to call upon the chairperson of SRC 2020, Professor KL Vaishnav, to deliver the concluding remarks on the behalf of the organizing committee as well as on the behalf of Department of Electronics and Communication Engineering. Professor KL Vaishnav, please.
Yeah, very good evening to our director, sir, Professor Shivaji Bandyopadhyay. Very good morning to Professor Antar from Queen University, Canada. Very good evening to Professor Ashok De from Delhi Technical University. My dear colleagues, Professor Upendra Kumar, Dean, other students, and esteemed speakers of this conclave, other listeners. So on the behalf of Department of Electronics, really we are very happy that over the last 3 months, that is Spark really have given really good, wonderful platforms. And we have seen that number of workshops they already conducted. This is the really another platform given to the PhD scholars, because this is a great opportunity. They can connect themselves then they can see the new horizon, because there are still students that are doing their PhD, but in the coming years they'll be completing, they'll be joining the job, and these connections really can leverage more things. So the Sparks, really I'm thankful to the Sparks for giving the opportunities to students, to the listener. Really, this area is so wonderful, as I already said at very beginnings, and other program also, that is a very much versatile and really interdisciplinaries. There is a circuits, that's many things, signal processing comes, many things comes into play. So we can really think of many people, even people from industry, they can join, because finally we need now products. So the commercial products maybe not possible, at least we can have sort of, so the prototype products, so that we can really look into the industry side, and tomorrow industry will be attracted toward the this side. This program really generating so many people, so many, and encouraging so many human resources, because those students, those listener, they will really maybe motivating many others, as few of the observer or few of the participants already mentioned that Divakar Sharma really is an undergraduate student. The way he said that really these workshops or this conclave really unfold many opportunity, and he had a lot of curiosity to know more on that, and that's the curiosity really will lead the really something new things. So I thankful to again to entire team, the Spark, Professor Antar, Professor Ashok De, and Dr. Taimur Khan for taking this initiative, because last 3 months hectic schedule is going on, and again in the month of January they have already planned one conference. Really the big task for this big job, I believe so, from the part of the Sparks. So I congratulate to everyone, especially the entire team of this Dr. Taimur Khan, because the back end of these online programs, online activities, there is a lot of manpower is needed, and over associated with this Dr. Noresh and then Partho, so many people, and our own PhD scholars. I'm very much thankful, and with our really full-hearted congratulations to them for completing this workshop in time, timely, and successfully. With this, thank you all. Have a good night, and over to Dr. Taimur Khan.
Thank you, sir. Thank you very much. Now, before concluding the valedictory session, I request everyone to please unmute your video just to take a group screen print along with all of you. Please unmute your video for a couple of seconds only.
Hello, sir.
Yes.
One more thing. Sorry for the disturbance, sir.
Yes, please.
Yes, sir, you were given one lecture, sir, EPC sector and antenna applications in one engineering colleges. Koku engineering colleges. One month before, sir. 1 or 2 months before.
Okay.
And that lecture is very nice, sir. You are so. I attended very clearly, sir. You are so talented, sir. The EPC sector is you are explained very well, sir. I understand very clearly, sir. Thank you, sir.
Okay. Thank you very much for that. Professor Upendra Kumar, sir, if you are there, please unmute yourself. Yes. Thank you everyone. Now finally, I on the behalf of organizing committee of SRC 2020, thank you all once again for being with us in this valedictory session. It has been really a great experience for using this digital platform in the ongoing COVID-19 pandemic situation. Now before saying you all final bye-bye, I would request to the registered participant for submitting the overall feedback of SRC 2020. With this, I conclude myself and bye to all. Good night, good morning, good afternoon to all of you. Stay safe.
Thank you, sir. Good night. Good night, sir.
All the registered participants, please submit the online feedback for the entire 5 days. The link will remain active for next 10-15 minutes.